Hey everyone, welcome to homework 4.4. So part A here says, describe how the values of each expression change as x increases. So don't forget to do this, right? So expression for 10 to the power of x squared, it is going to increase each time, but by a different amount. Whereas 2 to the power of x will increase by a factor of 2. Now here for this part it says, predict which expression will have a greater value when x is 8. So which of these will have a greater value when x is 8? Well, you know that x squared or 8 squared is 64. This would be 640. And then you're thinking about comparing 2 to the 8th power. But for this part, you're just predicting. So you can select whatever you want to select. So for this section right here, you pick, all right? There's no right or wrong answer. I just want to see that you actually chose and that you thought about which one you think would be have a greater value when x equals 8, 10, and 12. All right, so then it says find the value of each expression when x is 8, 10, and 12 and complete the table. Make an observation about how the values of the two expressions change as x becomes greater and greater. All right, so if I were to plug in 8 here, 8 times 8 is 64 times 10 is 640. 2 to the power of 8 then is going to be 256. Let's cue, this would be 1,000, but because we have 10 times 10 is 100 times 10 is 1,000. And then we'd have 2 to the 10th power. Let's go ahead and cue our calculator here. 2 to the 10th power is 1,024. Ooh, so now we have it being greater than. This is 12 times 12 times 10, 1,440. And then 2 to the 12th power is 4,096. So it's now gone and increased quite a lot. So here, notice that every time we are multiplying by a different number and adding a different number, right? So this is plus 30, this is plus 50, this is times 4, and this is times like 2 point something, right? And so the thing to notice about a quadratic function is that it doesn't increase or have the same factor when we're looking at our increase in y values, versus this one is times 2, times 2. We're adding different amounts because this isn't a linear function, but we're multiplying by 2 each time. So this is what you want to be able to notice. So 10x squared increases by different amounts and different factors, right? 2 to the power of x increases by a factor of 2 or doubles. So that's why when I'm telling you for the exponential functions, you can look at your y values to find out what the factor is. But for a quadratic function, you need to look at the relationship between x and y, right? How is x squared, and then how is that being changed to create y? In this case, it's then being multiplied by 10. All right, function f is defined by f of x equals 1.5 to the power of x. Function g is defined by g of x equals 500x squared plus 345x. I'm going to pause here because I have two special guests who are going to go over this one with you.
Hey guys, another video with Ben with quadratic functions, and we're going to be doing number 2 here. Okay, which function is quadratic and which one is exponential? Okay, here we have g of x is obviously quadratic because we got this little squared term right there. And f of x is obviously exponential because it has that little thing. So, g of x is quadratic. This is really hard. And f of x is exponential. Okay, the values of which function will eventually be greater for larger and larger values of x? Well, obviously, the exponential function will eventually be greater because it's exponential. So, f of x will eventually be greater. This is hard. Okay. See you later.
All right, well, hopefully you enjoyed that little cameo from Ben. Let's go ahead and create the table here to show this. So we're looking at our x inputs, and then we're looking at 3 times 2 to the power of x versus 3x squared plus 2x. And we want to show that this exponential function will eventually outgrow our quadratic function. So let's take a look at our calculator, and let's go ahead and put these two functions in here. So the first one, make sure I have the function correct, it was 3 times 2 to the power of x, and then, let me make sure, 3 times 2 to the power of, yep, and then 3x squared plus 2x. So 3x squared plus 2x. All right, so second table, and now we can compare our tables here. And so we can see that although this one initially starts off, well, actually, it looks like it starts off greater in some spaces and then slowly, but eventually it gets much, much bigger here at about 9. Okay, you have to wait your turn. I'm still doing this one. All right. So you can use this table to create your own table over here. I probably should have moved this over a little bit so that I could write at the same time. But 0, 1, 2, 3, 4, 5. And then you can keep going through those. So 3, 0, 6, 5, 12, 16, 24, 33. So it's less than still here, 48, 56. And then all of a sudden we go to 96 and 85. And then after that point, it continues to increase. So I'm just going to keep going here, 192 versus 120. 384 versus 161. So you can see at around the 5th value is when we start to see that bigger increase happen, and our exponential expression eventually overtakes that. So all you need to do for number 3 is complete this table. Number 4, the table shows the values of 4 to the power of x and 100 times x squared for some values of x. Use the patterns in the table to explain why eventually the values of the exponential expression 4 to the power of x will overtake the values of the quadratic expression 100 times x squared. So the reason is because we have a factor of 4. So because 4 to the power of x is exponential, we are multiplying by 4 repeatedly, and this will eventually outgrow 100x squared. All right, number 5. Here is a pattern of shapes. The area of each small square is 1 square centimeter. What is the area of the shape in step 10? So in this situation, we're looking at having 2 squares, then 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. So we see that we do not have the same factor each time. We are also not adding the same amount each time. So that means that this has to be quadratic, and we need to figure out what the quadratic function will be. All right, so I want to, of course, look at something being squared, and step 1 has 1, and then we add 1, right? Step 2, if we look at this one, we have 2 times 2 is 4, and then we add 1, 2, 3. Step 3 has a 3 by 3, and then we add 1, 2, 3, 4, 5. So, what do we see that is happening here? Well, this is the same as the step number, but it is also just 1 here. This is the same as the step number, but also adding an additional 1. And then here we have adding the step number, but adding 2. So if we want to try to figure out what's happening, we can also see that we have subtracted something. So on this one side, we would have n plus 1. Right? On this other side here, we would also have n plus 1. So n plus 1 times n plus 1. But then we are subtracting 2 minus 2. Same thing here. We subtracted 2 here. Okay? So this point right here, we're adding n squared plus n plus 1 plus, actually not n plus 1, sorry, just n plus n, because we're adding this here, plus n plus this additional 2 here, right? So you're trying to keep track of what you're calculating with your squared term plus the additional amount. So I'm going to just delete that so you can see a little bit better. Right here, we're adding a row of n, so that's plus 3. And then here, we're adding a row of 2. But here, we added a row of 2, which is n, and here we only added 1. So we're adding an additional n minus 1. All right, so you can also rewrite this as n squared plus 2n minus 1. And that should get you everything. So let's try that out. If we do 1 squared is 1, plus 2 is 3, minus 1 is 2, right? 2 squared. 2 squared is 4, plus 4 is 8, minus 1 is 7. That's correct, okay? And then both of these I do want to say are equivalent, and I'll be able to show you a little bit more as we get further into quadratics how that is equivalent. But you can also look at it as this n squared plus this row of n plus this row of n minus 1, so 3 minus 1, right? So that's where I got that from. And so in step 10, it would be, so earlier I actually made a bit of a mistake, so don't ignore this. Okay, all right, so it would be 10 squared plus 2 times 10 minus 1. So that is 100 plus 20 minus 1 is 119. And you can see that I drew this out here as well in a similar pattern as this, where we have 10 by 10 plus an extra row of 10 plus a row of 9 that's going across here. And so this would be 100 plus 10 plus 9 is 119. Okay? So the area of the shape in step n is this equation, n squared plus 2n minus 1. And explain how you see the pattern growing. So we see a base of 10 by 10, or a base of n times n, plus a row of n, and then an additional n minus 1 added to the top, right? So in this case, a base of 10 by 10 plus 10 plus 9. All right, number 6, a bicycle costs $240 and loses 3/5 of its value each year. This is a review, so we're going to write expressions for the value of the bicycle in dollars after 1, 2, and 3 years. So remember that if it loses 3/5 of its value, it retains 2/5 of its value. And you can also think of that as 40%. So if you wanted to, you can also think of that as a decimal of 0.4. And so our expression is 240 times 0.4. Again, what remains? And then to the power of 1, 240 times 0.4 to the power of 2, and 240 times 0.4 to the power of 3. When will the bike be worth less than $1? So let's go ahead and again use our calculator for that. You could continue to calculate that as well, but it's a lot faster to use technology here. So if we have 240 times 0.4 to the power of x, second table, we want to look at when is it going to be less than worth less than $1. That will happen in the 6th year. Will the value of the bike ever be 0? Explain your reasoning. So technically no, but it will keep getting closer, right? So if you look at, for this situation, right, it's down to like 0 point nothing cents, right? But it's not getting to 0. And if we were to look at the graph, we would also see that it comes down and it's getting closer and closer to 0. We zoom in on that, and then let's actually just make our window 0 to 20, let's say. Notice that it is getting closer and closer and closer to 0. All right, now, oops. Okay. Number 7 is a review of inequalities, and I'm going to keep putting these on your homework because it's important that you don't forget them. So a farmer plants wheat and corn. It costs $150 per acre to plant wheat, $350 to plant corn. The farmer plans to spend no more than $250,000 on both. All right, so this is our inequality. 150 wheat plus 350 corn has to be less than or equal to $250,000, right? No more than. The total area of corn and wheat the farmer plans to sell is less than, or plans to plant is less than 1,200. So wheat plus corn is less than 1,200. That's our second equation. It says the graph represents this inequality, right? So that's what we just created, which describes the cost constraint. Let W represent the number of wheat and C represent the number of acres of corn. This inequality, which I wrote above, represents the total area constraint of the situation. On the same coordinate plane, graph the solution to this inequality. So we need to graph this one. So notice that here C, corn, represents the y-axis. So I'm going to solve for that. C is less than negative W plus 1,200. Subtracted W from both sides here. So that's how I got that. Just a little review of equations or inequalities here. Subtracted the W. That cancels out. We have C is less than negative W plus 1,200 or 1,200 minus W. It's the same thing. Okay. Now, that means then that our y-intercept is going to be 1,200. So the corn will be 1,200 when the wheat is nothing, right? And so that would be up above here, which that's not very wise that they didn't give us enough space here, but that would be up here. And then similarly, if I don't plant any wheat, or if I don't plant any corn, then my wheat would be 1,200. So then my x-intercept would be, this is 200 here. All right. And so then I'm going to go ahead and use my ruler. Let me make sure that it's lined up as best we can line it up straight as it can be. That's pretty good. And so then we would have a dotted line here because it's less than. All right. Now it has to be less than 1,200. So the side we're going to shade will be underneath the line because 0 plus 0 would be less than 1,200. And if we were to do, for example, 1,500 and 1,500, that would not be less than 1,200. Okay, and so now the double shaded area is our solution set. It says use the graphs to find at least 2 possible combinations that the farmer could plant. So anything in this zone is fine, right? This is 200, 200 would be fine. This is 500, 400. So 500 acres of wheat, 400 acres of corn. So you can list out any there that you would see, but you want to find 2 possible combinations of corn and wheat and list those out for me. Again, using that graph. The combination of 400 acres of wheat and 700 acres of corn meets one constraint but not the other constraint. Which one does it meet? So let's look at 400 wheat, 700 corn. So 400 wheat, 700 corn is here. So it doesn't meet the blue restriction. The blue restriction was the cost, and the yellow restriction that I highlighted and filled in was the acres. So it meets the acres, but not the cost. Meets acres, not cost, because it falls outside of the graph for the cost. Okay? All right. This is a good question that if you're still struggling with it, you're still confused about something, that you come and talk to me and ask me about it so you can practice it. All right. Today's code word is my guest speaker, Ben. So your code word is Ben. If you put Ben on your homework at the top of your paper, you can earn extra credit. Happy homeworking and see you tomorrow.